Okay.
Alright, so kinematics, where did I put my book? Here it is. 3E today. It's quite a big exercise. And so we'll make our way through it and then we'll leave you for the sort of weekend to polish it off. Could you be able to someone shut the door there? Could you shut that? Thank you. Alright, so we've got a couple of things to cover here. Firstly, we use S for displacement, obviously, makes sense, right? And what we've got is some displacement function with regards to time. Now there's a key difference between distance and displacement. Displacement means how far is it from the origin. Okay, that's the magnitude of an object from its point of origin. Distance is how far it's moved in total. So the example we've got, all right, is Peter, if he's walked 20 metres east and then 15 metres back to the west, okay, 20 metres east, 15 metres back to the west, his displacement from his point of origin is only 5 metres. Okay, that's his displacement, but the total distance that he's walked is going to be 35 metres. Okay, so a key difference there between displacement, distance from origin, and distance, total distance travelled. Okay, what else we've got? Speed. So then velocity, right? Remember, if you differentiate displacement, you're going to have S dash of t. That is the rate at which displacement changes. Rate of change of displacement. That's going to be how fast it's moving. That's the velocity. And then acceleration is just the rate of change of velocity. So that's the link we're making here. Let's get straight into it. We've got the position of a particle moving along the x-axis. So we have a two-dimensional, two dimensions. It's moving along one axis. It's one-dimensional. The position of a particle moving along the x-axis is given by this this function, S of t. Draw a sign diagram of the particle's acceleration and velocity functions. So that means first we need to find the velocity function, right? Well, the velocity function is equal to the displacement function, the derivative of the displacement function. So that's going to be 3t squared, take 18t plus 15. Alright, so that's the velocity function. And from here, we could just put this in our calculator and graph it. I'm going to process it manually. I'm going to reflect those algebraic processes that we're getting pretty familiar with. So I want to find the roots of it. I'm going to factorise 3 first. Okay. And then if I want to factorise this quadratic, all right, I'm looking for 2 numbers that multiply together to give me positive 5 and add together to give me minus 6. And that's going to be minus 5 and minus 1. Okay, minus 5 times minus 1 is positive 5. And minus 5 plus minus 1 is minus 6. I think I just said minus 5 times minus 1 is positive 5. Minus 5 plus minus 1, negative 6. Okay, so displacement functions like that. If we want to know its roots, we're going to make it equal to 0, right? And so the solutions are 5 or 1. So over here, I'm going to draw the sign diagram of the velocity function. Now, with kinematics, when we draw a sign diagram, we have a line here at 0. Remember, we're only considering positive values of time. Okay, I'm only considering positive values of time. So this is 0. All right, that's where the sign diagram begins. All right, and we have a root at 1 and a root at 5. It is a quadratic, it's opening upwards, so we have a positive a value. So this is the sign diagram of the velocity function. And what this tells us, okay, if it has positive velocity, it's moving to the right. If it has negative velocity, it's moving to the left. Okay? And so what this tells us is this object we've got here, it starts moving to the right, it stops, and then it's moving to the left. Okay, so it has to stop there. The velocity is 0 at that point. Okay, and then it's moving to the left until time is 5, and then it starts moving back to the right. Okay, so that's what the velocity sign diagram tells us. and we found those roots there. I said we could go straight from here to here using our calculator, right? Graph that function, g-solve the roots, only consider positive values of time. Okay, so that's the velocity function. It asks us to find the acceleration function and draw its sign diagram. So when I differentiate it then, I've got it in these two forms, right? I've got it here expressed in general form, here expressed in root. I'm going to differentiate this one, because that's just going to be using simple differentiation. It's going to be 6t take away 18. All right, this is the equation of a line. It's got positive slope. The root is going to be 3. All right, so, you know, we can make the argument if you want to, but here is the root. This is the acceleration function, and it goes from below to above. Okay, so that's what part A says to do. Draw sign diagrams of the particles, acceleration and velocity functions. Done. Okay. Even in there, like we're only really getting the marks for this part and for this part. And so what you could even do is graph this function, you could graph the derivative without even finding the derivative, and just go straight to the sign diagram from it. Okay, part B. Find the position and time. Position and time when the particle changes direction. Okay, so it's changing direction, right? Look, remember, this velocity diagram tells us that. It's moving to the right and then moving to the left. Positive velocity, moving right, negative velocity, moving left. So it changes direction when time is 1, and then it's moving to the left, it starts moving to the right at 5. So to answer part B, changes direction at t is 1 and t is 5. Now that's the time where it changes direction, but it also wants the position. What's its position? What is its displacement? Its position with regards to 0. And so we can calculate s of 1 and we can calculate s of 5. All right, so when I'm doing that, right, if I want to calculate s of 1 and s of 5, and let's say I haven't even graphed it yet, for me to type this out, putting the number 1 in, and then type it out, putting the number 5 in, it's going to take twice as long. Okay? A better way to do it is to graph it and to g-solve. What is the y value when x is 1? What is the y value when x is 5? Although it is quite easy to substitute 1 in anyway, right? Because it's not change, it's just 1 take 9 plus 15. All right, with a graph function, x to the 3 take 9x squared plus 15x. All right, and remember it's time, so I'm only considering positive values of x. And I want to know when time is 1. I've got 7. And when time is 5, I've got minus 25. And if you've graphed the displacement function, okay, if you've graphed the displacement function, I'm just doing a really rough sketch of it. Here's what's going on. It's doing something like this. Okay? And this is the point when time is 1 and the displacement is 7. And this is the point when time is 1 and the displacement is minus 25. And of course we expect that to be the case, even if we hadn't given it the context of velocity and acceleration, right? This is the derivative of this function. This tells you the location of the turning points. There's a turning point when time is 1. There's a turning point when time is 5. Okay? When it makes sense in the context of moving to the right, okay, because it has positive slope, moving to the left because it has a negative slope. All right. Okay, so draw sign diagrams of the particles, acceleration and velocity. Done. Find the times and positions when it changes direction. Done. Okay, part C. When is the particle's speed increasing? Okay, so here I'm going to take you to the bottom 2 dot points. All right, important points. Bottom 2 dot points. Speed of an object is the magnitude of its velocity. So that means speed does not consider direction. Right? If you're doing physics, you're familiar. Velocity is a vector, speed is a scalar. It doesn't have direction, it's the magnitude of how fast it's traveling. If v of t and a of t have the same sign on the sign diagram, speed is increasing. If they don't, speed is decreasing. So the same sign. So let's look here. Between time is 0 and 1, the velocity is positive, but the acceleration is negative, which means speed is not increasing. Between time is 1 and time is 3, they're both negative. They both have the same sign, which means speed is increasing over that interval. Speed increasing. I'm going to write the whole thing up. When b of t and a of t have the same sign. Okay, so that's between 1 and 3. Right, between 1 and 3, they're both negative. And then, all right, if we look between 3 and 5, they're opposite. Okay, so speed is decreasing over that interval. And then after 5, speed is increasing. So we've got that statement and that statement. T is larger than 5. Okay, that's when speed is increasing. How about when is velocity increasing? This one's easier to answer. Velocity is increasing if the acceleration is positive. When is acceleration positive? For values greater than 3. Okay, so that was, to answer part 1, we used the third dot point. To answer part 2, we're using the fourth dot point of the important points. Okay, so we're reflecting on. Okay, part D. Find S of 6 and draw a motion diagram over the first 6 seconds and hence calculate the total distance. Alright, so first it says find S of 6. So that means when time is 6, what's the displacement? Well, remember I said let's graph this function. It's going to be useful because now I'm going to use it again. I'm just going to trace along it. When time is 6, what's the displacement? I've got minus 18. Okay, so that's finding S of 6. That's the first part of D. And in fact, what I'm going to do, for me to make a motion diagram, I'm going to list all of the important points. I need where does it start? All right, I need where does it change direction? We've already calculated those in part B. And then where does it finish? It starts when time is 0. It changes direction here. That's what we found. And then this is where we're asked to finish. It says after 6 seconds, that's where it's going to finish, or that's when we'll stop assessing it, in the first 6 seconds. All right, so we saw S of 6 is minus 18. We had S of 5, we can look over here, minus 25, 7. We haven't calculated S of 0, but look at the equation. If you put 0 in there, S of 0 is 0. It starts at the point of origin. That's its initial position. Okay, so we're going to draw a motion diagram. A motion diagram is a horizontal axis that displays displacement. So where people sometimes get confused is, hang on, our sign diagrams here, they're only positive. This is time. We're now drawing an axis that has displacement on it. And I'm thinking about this axis and I'm going, all right, what's the value furthest to the right? Okay, the largest value here is positive 7. So I'm going to put positive 7 there. And what's the value furthest to the left? It's minus 25, so that's going to be there. And then I'm just going to fill the other parts in approximately. The scale doesn't need to be perfect here because we're only using it to answer the question about the total distance. All right, that's its utility. Minus 18 and then 0 is about here somewhere, right? Okay, so we've got the axes and we've got the important points there. Now, draw the motion diagram. Okay, it starts here. Okay, when time is 0, the displacement is 0. That's where it begins. We're putting a dot there. And initially, it's moving to the right. Okay, after 1 second, it is at S of 7. So it's coming up here. Is at 7 meters. After 1 second, it is 7. Are we given meters? Meters. It is 7 meters to the right of origin. Okay? And then it starts moving to the left, right? We have this big period, 4 seconds of negative movement to the left until it gets to minus 25. All right, so that's going to be our S of 5. Okay, and then it's moving to the right for another second, where it finishes, S of 6. Okay, or we can draw an arrow there to denote it's going to continue with positive direction, positive velocity. Okay, so notice how we've got an axis and we're just stating its position with regards to time. You can think of, like, if this is a graph, we've got displacement on here and then we've got this sort of time going on there. It's not scaled, but we're just demonstrating as you move up, it displays time moving forward. Time is 0, time is 1, time is 5, time is 6. Okay, so we've drawn the motion diagram, done. Hence, find the total distance travelled in the first 6 seconds. Because if I was to ask you what's the displacement after 6 seconds, well, that's where it finishes, right? The displacement is 18 metres from the point of origin, all right? What is the total distance? Well, we can see it's moved 7 metres here, so that distance is 7 metres. And then we can see it's moved 25 plus 7. This whole distance here is 32 metres. All right, and then we can see it's moved 7 metres here as well. Okay, so the total distance that's been travelled then, 7 plus 32 plus 7, is that 46 metres. All right, another way to do it without the motion diagram is the total distance is S of 6, take S of 5. Okay, so that one plus S of 5, take S of 1, plus S of 1, take S of 0. Okay, cool. So that's, we've answered the problem, hence find the total distance travelled in the first 6 seconds. Very good. All right, let's move on to the next one. This one's pretty similar. So, how about I stop there, I'll leave you guys to have a go at this problem and do this one first and then we can move into the exercise. All right? So have a go at this problem and then we'll move into the exercise.